Hello everyone, let's analyze. So today we're going to talk about accumulation points and the Bolzano-Weierstrass theorem. So before we get into what those things are, let's just consider a sequence. Suppose I have a sequence AN where the even entries are 1 over n and the odd entries are 2n plus 1 over 3n minus 1. Now, the sequence is bounded. It never gets below 0, and it never gets greater than 3/2. So 0 is a lower bound on the set of sequence values, and 3/2 is an upper bound on the set of sequence values. Now, while the sequence is bounded, it is divergent. However, there is a sense in which 0 and 2/3 behave similarly to limit. Now, what's special about 0 and 2/3? Well, the even entries converge to 0, and the odd entries converge to 2/3. But the sequence as a whole does not converge to any limit. Because, of course, we know that if a sequence has a limit, that limit has to be unique. So the way that 0 and 2/3 behave similarly to limit is that every neighborhood of 0 contains an infinite number of sequence entries. Specifically, because we know the even entries converge, all but a finite number of even entries are contained in every neighborhood of 0. And every neighborhood of 2/3 contains an infinite number of sequence entries, specifically all but a finite number of the odd entries. But neither neighborhood, could we say, contains all but a finite amount of entries if the neighborhoods don't include the other point. But 0 and 2/3 certainly seem special in some way to the set of sequence entries. What should we call them? Well, we can call them accumulation points. So let S be a set of real numbers. And notice a key part of this definition is that we're talking about sets. Sets have accumulation points. A real number A is an accumulation point of the set S if and only if every neighborhood of A contains infinitely many points of S. Notice in the definition, nowhere do I require A to be in the set S. That's not required. So as an example, consider the set of values AN, where AN is the sequence we defined on the previous page. Now, we know that the sequence 1 over n converges to 0, and we know that the sequence 2n plus 1 divided by 3n minus 1 converges to 2/3. And we also know, or we could show, that the sequence entries don't repeat. So I have infinitely many different sequence values. So therefore, all but a finite number of set elements corresponding to n being even are in any neighborhood of 0. Meaning every neighborhood of 0 contains an infinite number of values, since the sequence doesn't repeat. The exact same can be said of all neighborhoods of 2/3 and set elements corresponding to n odd. Therefore, both 0 and 2/3 are accumulation points. So, oh yes, you in the back, yes, you have a question? With the blue shirt, yes. When can we be guaranteed of an accumulation point? Well, I'm actually glad you asked that question. The Bolzano-Weierstrass theorem is such a guarantee. It guarantees that every bounded, infinite set of real numbers has at least one accumulation point. So before we get into the proof, let's take a look at the idea behind the proof. So consider the set of numbers generated by the recursion, the new entry is 1 plus the reciprocal of the previous entry, where the first entry is 1. So x1, as we can see, is 1. x2 is 2, 1 plus the reciprocal of 1. The next entry would be 1 plus the reciprocal of 2. Now, we've seen this sequence of values before. Now we're considering them as a set of values. So there's x4, x5. Now, we know that this is going to converge. We actually haven't proven it yet, so maybe we don't know. We've taken it on a matter of faith, based on previous lectures, that I told you it converges, and of course, hopefully you all have great faith in what I say. Or maybe you don't, and that's why I have to prove everything I say. x6, x7, x8, x9, x10, 11, 12, so on and so on, forever and ever and ever. They certainly do appear to be localized around a limit. And of course, we can take this forever and ever and ever and ever. And let's just suppose that that's already been done. That in just a few seconds, I plotted an infinite number of red dots. Let's just suppose. Now, this sequence is bounded between 1 and 2. There's infinitely many values. This sequence doesn't repeat. We could prove that. We haven't, but we could. So Bolzano-Weierstrass guarantees that there's an accumulation point. And as you might imagine, the accumulation point of this set of numbers would be the limit of the sequence. Now, how would we prove that in general? How would we even illustrate such a proof for this set? Well, I could cut my set in half, and I've got two intervals, 1 to 1.5 and 1.5 to 2. One of those intervals, at least, must contain an infinite number of values, and it's the one to the right. So let's zoom in there. I could cut that in half, and one of those intervals must contain an infinite number of values. It's the one to the left. I could take, after zooming in, the halfway point. One of my two subintervals must contain an infinite number of values. It's the one on the left. So let's zoom in, and let's repeat this process forever and ever and ever and ever. Now, notice that every new interval I get is shorter than the previous, specifically half as short. Furthermore, if I look at the left-hand side of each new interval, it is further to the right of where I began. Right? I began at 1. And the right-hand limit of my interval is further to the left of where I began. Remember, I began at 2. The left hand of the interval doesn't move unless it moves to the right, and the right hand doesn't move unless it moves to the left. So let's make sure that we notice this as we continue. So again, I take my interval, I cut it in half. The subinterval of length half the previous to the right has an infinite number of values, so I zoom in, cut in half. The right side contains infinitely many values, cut in half. Right, again, we have these set of intervals which are nested or inside of the previous interval because it's half of the previous interval. So I can keep going. Because each new interval is half the previous, I can actually make these intervals arbitrarily small. The idea behind the proof is that any neighborhood around an accumulation point must contain one of these subintervals as I continue to go, because these subintervals get, well, arbitrarily small. Let's cut in half again. It's the one on the left. Cut in half again. The one on the right. Cut in half again. It's the one on the right. Now, I can keep going forever and ever and ever and make these subintervals arbitrarily small. And that is the central idea or concept behind the proof. So now let's give a formal proof. Let S be bounded and infinite. Now, by the least upper bound axiom, the set has a supremum. And by a theorem that follows directly from that axiom, it must also have an infimum. Furthermore, the set has to be in the closed interval A0 to B0, because B0 is an upper bound and A0 is a lower bound. Now let C be the midpoint of this interval that contains my set. Right, again, we're going to take that interval and cut it in half, just like we just saw in the illustration. And as we saw in the illustration, either the interval A0 to C or C to B0 contain infinitely many elements of S. At least one of them does, because S has infinitely many values. So we'll call that one A1 to B1, whichever has infinitely many values. It's the interval that we zoomed in on in the illustration. So let's repeat the process for A1 to B1 so that A2 to B2 also contains an infinite number of elements of S and is half the length of A1 to B1. And let's just keep doing that forever and ever and ever. As I mentioned, what we're creating is a sequence of nested intervals, with the biggest interval being A0 to B0. So really we should read this sentence here right to left. This interval contains A1 to B1, which contains A2 to B2, which contains, well, so forth and so on. Because this is we could think as the mother interval, and this is inside of it, A1 has to be to the right of A0, and B1 has to be to the left or equal to B0. So B0 is the furthest to the right. Remember in the example we just showed, B0 was 2. Every subinterval that we looked at had a right-hand side that was less than 2 or equal to. So B0 is greater than or equal to B1, which is greater than or equal to B2, which is greater than or equal to forever and ever and ever and ever and ever. And all the B's are greater than or equal to all the A's, because the B's are the right-hand side of an interval. So A0 is the furthest to the left, then A1, which is equal or to the right. A2 is equal to A1 or to the right, and so on and so forth. So this order of infinitely many numbers is going to be important in our proof. And this ordering comes from the nested property. So it's important that you stop here and make sure that you understand this idea and rewatch the illustration to see it in action if you need to. Now each new interval is half the length of the previous interval, which itself is half the length of its previous interval, so on and so forth, meaning that the length or the distance from Bn to An is the original interval length divided by 2 to the n, which can be made arbitrarily small. In fact, we know that 1 over 2 to the n can be made arbitrarily small because, well, we showed that in our homework. Specifically, we can say that for any epsilon greater than 0, there's a natural number L for which BL minus AL equals B0 minus A0 over 2 to the L. This equality comes from this observation, and this is less than epsilon, right? For every epsilon, we can find an L that'll make this true, right? We can do that. And if P is any integer greater than or equal to L, then BP minus AP is also less than epsilon. Now let A be the supremum of the set of all left interval bounds. So A is the supremum of the set of all AN for every natural number n. So if I go back to my illustration and take the left hand of my interval and take all of the left hands as I iterated, that would give me a set of numbers. It's a set of numbers that are bounded. it's non-empty, so therefore it has a supremum. Well, then A is the promised accumulation point of S. Yes, you have a question? Well, how do I know that A is an accumulation point? Oh, actually, that's a really good question. Well, here's how I know. From the no sunshine definition of supremum, there exists an element of that set, AM, which is to the right of A minus epsilon. And this is true for any epsilon, right? This epsilon is for any epsilon in the previous page. If I go from A any amount to the left, then I have a set value to its right, which is, of course, bounded above by A because A is an upper bound. It's the least upper bound. So this is just stating the no sunshine definition of a supremum. Now let P be either L or M, whichever is bigger. Since M is less than or equal to P, A minus epsilon is less than AM. That follows from this no sunshine definition. AM is less than or equal to AP. That follows from the nested observation that my left-hand side always moves to the right. And that's less than A because A is an upper bound. Furthermore, since P is greater than or equal to L, well, if P is greater than or equal to L, we know precisely what the consequences are. It's this. So that's what we have written here. Note that inequality 4, this one, implies that BP is less than AP plus epsilon. How do I know that? Well, I just added AP to this and to this. Now, how do I know that AP plus epsilon is less than A plus epsilon? Well, because AP is less than or equal to A. Which means this should be a less than or equal to. So you'll have to forgive me the typo, I hope. Now, putting our conclusions together gives A minus epsilon is less than AP. A minus epsilon less than AP. AP is less than BP. Right? That's because AP is the left side of an interval and BP is the right side of an interval. BP is less than A plus epsilon. We have this observation here. So this set of inequalities means that the closed interval AP to BP is a subset of the epsilon neighborhood of A. That is the open interval A minus epsilon to A plus epsilon. Recall that the closed interval AP to BP, which is contained in the epsilon neighborhood of A, by its very construction contains infinitely many entries of S. The fact that epsilon was arbitrary means we have satisfied the definition of an accumulation point. And I rest my case. An immediate corollary to this result is that if a sequence has a finite number of repetitions and converges to A, then A is an accumulation point of the set of all sequence values. Well, that's it for today. Oh, what about Cauchy sequences? Do they converge after all? Is convergence and Cauchy the same? Well, we're getting there. I know, the suspense is killing you, but stay tuned. We will get there.